Welcome to lesson 4. We're going to look a little bit closer at permutations. So we're going to look at a few different scenarios, just lots of more permutation questions. So the first ones, which really we've kind of looked at already, is items from a distinguishable set. So all of the objects in the set are different. So let's just get right into it. This is kind of what we already know. So if you were given a ballot to vote for school council, and there's 5 people on the ballot, and the positions are president, vice president, secretary, treasurer, and social coordinator. So I've got 5 positions in total, okay? And I've got 5 people on my ballot. So how many ways can you fill out the ballot if you're going to vote for everybody? So basically, if we were going back to fundamental counting principle, that would be, I would have my 5 positions, president, vice president, secretary, treasurer, social coordinator, and I would have 5 options for that person, then 4, then 3, then 2, then 1. Or we can say that I have 5 people to choose from and I'm going to pick 5 of them. So 5p5. Either way, I get 120. How many ways can you vote if you're only voting for president, vice president, and secretary? So again, I have 5 to choose from. I'm picking 3 of them. So 5p3 gives me 60. You could also do your 3 positions, 5, 4, 3. In how many ways can you vote if you're only going for president and vice president? So from 5, I want to pick 2 of them. So 5p2 is 20. And just for president, pick just 1 out of the 5 is 5. Okay, so that's fairly self-explanatory. We've already looked at questions like that. Let's look now at permutations with identical objects. So what happens here is that there's repetition. So for example, if I had 5 marbles in a bag, 3 are red and 2 are blue, it's repetition. Okay, so to solve permutations like this, my formula is n factorial, where n is the total number, divided by r factorial, s factorial, t factorial, where r, s, t, whatever the letters are, the quantity of repeated objects. Okay, so let's take a look at this example. In how many ways can the letters in the word Saskatoon be arranged? Okay, so we'll just do that first, just arranging Saskatoon. So you count up the letters in that word, first of all. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9 letters altogether. So this has an A and a B part. It'll be 9 factorial. Then you go through all of your repetitions. So there are 2 S's, so 2 factorial. There are 2 A's, so another 2 factorial. And then there are 2 O's, so another 2 factorial. So 9 factorial divided by 2 factorial times 2 factorial times 2 factorial. We can put that into our calculator. We get 45,360 ways to represent the letters in the word Saskatoon. The second part of this question says, in how many ways can they be arranged if the word must begin and end with S? So in my 9 letters, 1, 2, 3, 4, 5, 6, 7, 8, 9, I must have an S at the beginning and an S at the end. So there's one way to do that and one way to do that because we can't tell them apart. And then for all of the middle ones, I've got 7 letters left. So 7 factorial divided by, my S's are out, but my A's and my O's still repeat. So it ends up being 1 times that times 1, which is 1,260. And how many different 9 block routes are there between point A and point B? You must go 4 blocks north and 5 blocks east. So 9 factorial divided by 4 factorial times 5 factorial is 126. Okay, let's look now at permutations with cases. So this is maybe the longest type ones. So for example, Billy needs a password that uses the digits 0 to 9 and or any letter, so you can have the digits 0 to 9, any letters in the alphabet. It's case sensitive, so that means that like lowercase and uppercase are different. So you actually have 10 things here to choose from, 26 capital letters, 26 lowercase letters. You must have at least 5 and a maximum of 7. So you could have 5 characters, 5 characters, or 6 characters, or 7 characters. So if you remember from the last unit on set theory, the word or means to add. So I'm going to figure out how I can pick 5 characters, right? So I've got a total of 62 items to choose from because the lowercase and the uppercase and 10, that equals 62. And I want to pick 5 of them. Or I could have a 6-character password, or I could have a 7-character password. Okay, those are huge numbers, so I'm just going to put that all into my calculator, and it comes out to actually be in scientific notation. So I'm just going to keep all of my decimals that my calculator says. 2.5236907 times 10 to the 12 different ways. So there's like 2.5 trillion cases that you could, different passwords that you could have. Okay, often you can still resort back to the fundamental counting principle if you want to. It doesn't really matter. Like there's more than one way to get to the end answer here. Let's look at this one. At a used car lot, 7 different models of cars are to be parked near a street. So I've got 7 cars. Okay, I'm going to park all 7 cars. The 3 red cars, but they're all different models. Okay, so I can't. I can, even though there's 3 red, I can tell them apart because they look different. Okay, so there's 3 red cars. They must be parked so that there is a red car at each end, and the third is exactly in the middle. Okay, so if I was to do this with fundamental counting principle, I would have my 7 spaces for my cars. 1, 2, 3, 4, 5, 6, 7. I know that I need a red car at each end and 1 exactly in the middle. So when I go to place that first red car, I have 3 of them that I can choose from, and then 2, and then 1. And there would be 4 other cars left that I could place in the other places. Okay, so that is equal to 144. So you can fundamental counting principle it. You could also, technically what this means is I have 3 red cars and I want to place all 3 of them where order matters. And then I have 4 other cars and I want to place them, all 4 of them. This also equals 144. So you can see it either way. The 3 red cars must be placed side by side. Okay, so this one, the way this works is I could then have a red, and a red, and then 4 other cars. Or I could have 1 car and then 3 reds, and then 3 cars. Or 2 cars, my 3 reds, and then 2 more. Or I could have 3 other cars and then my 3 reds, and then 1 more. Or I could have 4 cars and then my 3 reds, right? So each of these cases, so basically I have 1, 2, 3, 4, 5 cases. And if I was looking at how to line these up, so this would be 3 times 2 times 1, 4 times 3 times 2 times 1. So it'd end up being the 144 that I got in the first example, because it's like basically I'm lining up those 3 red cars in a specific order, and then I'm lining up the 4 other cars in a specific order, and I would do that 5 times and add them together, or I could just multiply by 5, right? So basically, if I was to figure out all of this, that is 144. That's what I got up top, and I would have 5 of those. So it ends up being 720 different ways to line them up side by side. So when there's cases, you're just going to have multiples that you have to add together. Alrighty, so you can go ahead and practice with some of these questions now.